I'd like to start out my talk with a story, if you don't mind. I had an art history class in college, and it was right after lunch. And this is an allegory. And I would come into class, and the teacher would turn the lights down, turn on the projector, put up slides of paintings. And he would talk in a monotone voice and say, this painting was painted in 1875 by this illustrator, and it was done in this style. Next slide. This painting was painted in 1937 by this illustrator in this style. Next slide. This became my nap time. I think there were maybe 2 or 3 of those classes that I didn't sleep in. Please don't do that. There's several parallels here, and I don't want you to go to sleep. Shaders are something that I'm very passionate about. I love writing shaders. I love talking about writing shaders. And I'm excited to share sort of a very basic level today with you guys of how to get started writing shaders. If you're already very experienced with this, maybe you can use this as your nap time right after lunch. Otherwise, please stay awake. I'd love to participate with you in learning how to do this. I'm Ben Cloward. I work at BioWare as a CG supervisor. That's my title, and basically it means an older tech artist. So by way of introduction, these are a few of the projects that I've worked on over the last 17 years. You'll notice that Star Wars: The Old Republic is maybe 4 or 5 times larger than some of the others. That's because I worked on it for 4 or 5 times longer than most of these other games. I've also been involved in a few other projects. Here, this is a screenshot from the original Shader Effects application that I wrote together with Case Reinen. Shader Effects was purchased by Autodesk, and now it's one of the core methods of creating shaders for real time in both Max and Maya. I was also involved in a series of training DVDs for teaching artists how to write shaders in HLSL. So today, we're going to go over some of the basic concepts about shaders, and then I'm going to go over 3 examples and kind of walk through how each of these examples is put together. There's nothing magical about the examples that I'm showing, and I'm not showing them because it's absolutely important that everybody know how to do these 3 things in shaders. But I chose these examples because there are elements in them that you can use that you can take apart and use to put back together to build other things. So while we're going through the examples, I don't want you to think in terms of I have to know how to create this specific shader, but more I need to learn these building blocks so that I can reassemble them to create the ideas and the shaders that I want to build. The examples that I'm putting together that I'm going to be showing in the slides are illustrated using the Unreal Engine's shader editor, the node-based shader editor. My work at EA, at BioWare, is done in Frostbite, but the 2 editors are so similar together. I didn't want to deal with approvals from my company, and so I just went home, downloaded Unreal, and I'd never used it before. But it was so similar to what I was used to at work that I was able to just get shaders up and running right away. And so that's what you'll see in the slides. I also like to write shaders in HLSL. I do both. And you'll see at the end of each example, I have a slide with the HLSL shader code that shows sort of the same thing in code rather than in the node-based shader editor. I'm not going to dwell a lot on the code because I don't want to make people afraid, oh no, there's code on the screen. But I do want to put that up there so that you can compare what does the shader node network look like and what does the HLSL look like. So the concepts that I'm going to talk about apply to both node-based editors and writing shaders in code. All right, so a couple of basic concepts that we need to talk about before we dive right into the examples. We need to define what a shader is, talk about what it can do, and then one really important foundational item is data types. So first of all, what is a shader? As a technical artist, a lot of the things that you do are only noticed if they're wrong or they're broken. For example, if you're doing skin weights on a character, nobody notices that, right? If you spend hours and do a beautiful job weighting your character, nobody's going to even mention that to you, unless there are 3 verts sticking out of the neck, right? And then somebody's going to be like, hey, fix this, it's broken. Same thing applies for tools and exporters. You know, people just assume the exporters are going to work, and they only come to you if there's some sort of exception thrown or something goes wrong. Hey, why is the exporter broken? It's not working. Shaders aren't like that. If you work on a cool shader, people are going to walk by your desk and go, oh, wow, that's cool, right? So that's one of the reasons that I like it. It's a way to do the art in technical art, right? A lot of the things that we do as tech artists focus on the technical part of that, and we're starting to lose the art part of that. Shaders are a cool way to do art with math, and that's another thing that I really like about it. So fundamentally, a shader is code or a node network that under the hood becomes code that defines what color every pixel on the screen is, and it usually runs on the graphics processor. So I want to talk a little bit about history. It used to be when shaders were first developed, you had a shader that did everything all together in one shader. But nowadays, game engines are using really advanced lighting models with physically based lighting. And a discussion of physically based lighting is kind of outside the scope of the talk. But what I do need to mention is that because of the complexity of the lighting portion of the shader, there's sort of a divide happening, and it's important that shaders, you know, there's the part of the shader that does the lighting, and then there's the part of the shader that does the surface properties. And that's especially true for rendering engines that are deferred, because the surface properties happen before the G-buffer, and then after the G-buffer, you have the deferred lighting. Anyway, that's getting really technical. I don't want to get too far into that. Most game engines have a built-in shader editor, which means that you can do your shader editing in a node-based network, like Unreal Engine or like Frostbite. And what you're editing is actually the surface properties of the object itself, and not necessarily the lighting. So this will help to illustrate that a little bit. There are a lot of different things that shaders can do. They can do the diffuse lighting. They can do the surface color of the object. They can do screen space ambient occlusion, you know, all kinds of different things. But really, there are just 2 big categories of what shaders can do. There are the surface properties of the object itself, and there are the lighting properties from lights in the scene and from ambient light and other things that are external to the object that's being rendered. So if we sort all of these things, we can see we have a category for surface properties and a category for light properties. Shaders do all of these things, but it's really helpful to sort them and understand the difference between the 2 categories. So it used to be when shaders were first introduced that a single shader would do all of these things. And we had sort of a really messy mix between what the surface was contributing and what the environment and lighting was contributing. You had light baked into the textures on the surface, and you had surface properties from the environment, and it was just kind of a messy mix between these things. And it's really important that we not mix light properties and surface properties. So we're just not going to do that. The reason that it's important to keep these things separate is if you create a model and it has lighting properties in it, for example, if you have a specific reflection map that's associated with your model, if you put that model in another environment, it's reflecting something that's not actually coming from that environment, and it doesn't work. If you have a nighttime scene and you paint all of the objects in your nighttime scene with sort of a blue tinted texture, then suddenly those objects only work in the nighttime scene, and you can't take them and put them in your really bright daytime desert scene, right? So it's important that we keep surface properties separate from light properties so that objects can be put in any kind of different lighting environment. And it's also important to keep lighting out of the surface properties. And the reason that that's important is because you want all of the objects in your game to be lit consistently, and you want your lighting model to be continuous and consistent across your product. You know, if it's daytime or nighttime, you want all the surfaces, or you want all the objects to feel like they fit together in a cohesively lit environment. So we want to make sure that we separate out those two things. So the shaders that we're going to talk about today focus on the surface properties. In an advanced physically based render engine, the engine takes care of all of the lighting properties, and generally these things are done by the graphics programmers. And you know, they're at SIGGRAPH, for example, there's a whole day-long session devoted specifically to physically based lighting and rendering, and those guys really geek out about, you know, how accurate their lighting models are getting, and you know, how well they can imitate exactly what light is doing in the real world, and we'll let them do that. What we want to do is write shaders that determine, you know, what color is the surface, how reflective is the object, is it metallic or not, these kinds of properties on each object. And then we'll let the game engine do the lighting. So the shaders we're going to focus on today determine the surface properties for the model. All right, that brings us to data types. So when you're writing your shader, it's important that you understand what kind of data you're dealing with. And what this basically means is I have a container. How big is the container, and what kinds of things will fit in it? So float is the first data type, and that's a container that will fit one value. So you can fit one thing in your container. Float 2 can fit 2 values. And usually we use float 2s for UV coordinates because you have a U value and you have a V value, and those things fit nicely into a float 2 data type or container. Float 3, there are 3 values, and we use these things for vectors because vectors have an X, a Y, and a Z component. So that becomes a float 3. And then for float 4, those are vectors that also have a 4th W component. Or it also works for colors with an R, G, B, and an alpha value, right? Red, green, and blue, and alpha. So when you're creating your shader, whether it be in HLSL code or GLSL or other shading language, or if you're using a node network, it's important to know when my value comes out of this node, what kind of, what data type is it, or how many things are fitting into that container so that I can connect that up and I know what kind of data I'm playing with. All right, so I hope those are a couple of foundational elements that will help you with your understanding as we move into our examples. So the first example that we're going to talk about is distortion. And this is something that you could apply to a surface if you wanted to, I don't know, distort it, make it feel all weird. It's also an example that you could apply this to the screen if you wanted to do some kind of heat haze and you wanted everything behind the heat to feel like it was all ripply. So let's jump in and talk about how to achieve distortion. So we're going to talk about 2 nodes just to begin with. The red one is texture coordinates, and then there's also a texture sampler. So I'm using a texture here that is a nice test grid, and it has the different colors in the corners, and it has a grid pattern on it. There's nothing special about this texture. I'm just using it so that you can see how the distortion is working. So every model, every object or mesh in the game has texture coordinates assigned to it, and those textures determine, or those coordinates determine how the texture is applied to the model. Really basic stuff for artists. But to build a shader out of these, and this is one of the most simple shaders, you just wire the texture coordinates into the texture sampler, and then plug the texture sampler into the base or root node of the shader. And then over here on the right side, this is what you get as your result, just the shader, or the texture as it is, right? So we're taking our texture coordinates, sampling the texture, and then passing that in as the result. Now what we want to do is play with the texture coordinates a little bit before we use them to sample the texture. So I'm going to introduce two new nodes. One is multiply, and this is just really simple math. And then the other one is a float to constant value. So here the values of the yellow node there are 0 and 0, but we can change these values and set them to whatever we want. So I'm going to add these two nodes into our simple shader. And what this is doing is, because I'm multiplying the texture coordinates by a value, we can scale the texture. So now I can tell it, I want to tile it 5 times, or I want to scale it bigger or smaller. So basic principle takeaway here is that the multiply node, when applied to texture coordinates, serves to scale the texture larger or smaller. And you can see here the animation on the left side. As the values change, the texture is scaling larger and smaller. OK, next principle, we're going to use add. This is really simple stuff. Multiply scales, and now we're going to add to the texture coordinates. And what you can see happening here is that as I change my constant value, the yellow node there, it's wired into the add. Actually, I guess I can just do it like this guy right here. So those values are changing. As they're adding, you can see the texture scrolling. And it's only scrolling in one dimension, right? And that's because I'm only changing the x value and not the y value. Okay, so the y value is staying 0, and the x value is changing, which makes the texture scroll. So the takeaway here is that when you add to texture coordinates, you get scrolling. So multiply scales, and add scrolls. Okay, some pretty basic stuff. Next node to add is time. And this is a node that the value just continuously goes up. So as time passes, the value gets larger and larger and larger. That's what the time node does. So we're going to add that into our shader node network. And here, I'm adding time to our texture coordinates. Before, you could see the texture scrolling. Well, that was just because I was changing the value really fast. But what time does is it basically is changing the value every frame. It's continuously passing. And so we're doing the same thing here that we did with the constant value, only it's updating every frame. And you can see that it's going diagonally, and that's because it's adding to both the u and the v values, right? So whereas before I was just changing one of them, now I'm changing both of them at the same time, so we get this diagonal movement. So now if I take my time value, this is one of the drawbacks to presenting using node-based networks is that it's really easy for these networks to go crazy. So I'm trying to keep these examples simple so the networks don't grow too big. But when you're building a system like this, it's really easy for the network to just turn into spaghetti. And when you're actually in the system itself, you can zoom in and out. You can focus on just one part of it and then zoom out and see the whole thing. But when you have them on a slide, it has to all fit on one slide. So I've tried to keep the network simple. What we're doing here is we're multiplying time by a constant value, and that slows it down. So it was scrolling diagonally before, but now I've multiplied time by 0 in the y and 0.5 in the x. So now in the x coordinate, I'm just scrolling at half speed, and y coordinate, I'm not scrolling at all. So I get the nice scrolling in one direction. Okay, now this is where it starts to get really complicated. I've built a noise texture basically with render clouds in Photoshop. And I've got render clouds made to tile, and I've got a different pattern in the X, Y, and the Z, or red, green, and blue channels, which makes this, this tiling noise texture. And then I'm also introducing a new node here called append, which allows me to put two values together. So if I have a float value and a float value, for example, and I use append, now I have a float2 value, a single value that contains both of them. So here's where I first start to get a basic distortion pattern. So what I've got is time here, and I'm multiplying it by the constant value that we saw before. And then I'm adding that to my texture coordinates, which is scrolling my noise texture. And then I'm using the red channel and the green channel of my noise texture and adding those together to make a float2. So all of this part right here is not for the purpose of applying to the surface of the model. It's only for the purpose of messing up the UV coordinates that I'm going to use to look up this texture. So when I presented this before, I had a bunch of students ask me, like, why don't I see this texture on the model? And the answer is you do, but you only see it in the way that the distortion turns up. So if you look really closely, you can see that the distortion pattern is scrolling through the other texture. Can you pick that out? It's like a looping scrolling pattern, right? You can see what I'm doing here. So I should probably explain this node too. This is a multiply, and the purpose of this multiply here is to really shrink down the size of my distortion. Otherwise, it would be so wildly distorted that you couldn't even make out what the texture looked like at all. And so I put this multiply here. I think I'm multiplying it by like 0.01 or something really small to shrink down the amount of distortion. And then I'm taking that distortion and I'm adding it to the UV coordinates here that I'm using to look up into my second texture. Well, this is pretty decent distortion, but like I said, if you look at it closely, you can see that scrolling pattern, and it's really repetitive. So if we want to break that up, we can go one step farther. And this is where the network starts to get really complicated. Basically, what I'm doing is I'm doing that distortion pattern here and then again here. And you'll notice that each of the times that I'm doing it, I have these different values, right? And so one distortion pattern is basically scrolling this direction, and the other distortion pattern is scrolling almost the opposite direction, but not quite. And the speeds are slightly different. And so they create sort of this, boy, I don't even know what to call it, like a resonance or like a, I don't know, you can probably think of a better term for that. But the two patterns are being added together here. And then we're using that, multiplying it again by a small value, and then using that to distort. And the result of that is you have two different looping patterns, but they're not looping at the same rate, and they're not looping in the same direction. And so you end up with a non-looping pattern. And so for the purposes of the video, so it wouldn't be super huge, this is a fairly short video here. But if I were to just let this play, you would never see a repeating pattern just because of the way that the times are set up. So that's my example of how to set up distortion. Like I said, you can set this up to make a surface look really weird, to do heat distortion. If you had a fire particle, you could apply this to your fire. All kinds of uses for distortion. And you can also break the shader up and use individual elements to make other kinds of effects. All right, so as I promised, whoops, skipped it. Oh, that's interesting. Jeff, that slide's not supposed to be in there. All right, as I promised, here's what the code looks like. I'm not going to stay on this too long, but you can basically see that I'm setting up two different distortion amounts and then adding those to my UV coordinates and then returning the results of the distortion added together. So this is written in HLSL. I haven't actually run this code. I just typed it in as it is. So if you download the talk notes and you run this and there's all kinds of bugs in it, send it to me and I'll fix them. I didn't actually try it. OK, the next example that we're going to talk about is Atlas Walk. And every exciting talk has to have explosions, right? So if you're sleeping before, this is where you wake up, because now we're going to talk about how to make explosions. What's going on here is I'm basically playing every frame of an explosion. And I'm going to go through the process of making a shader that displays each of the frames in order to make the explosion. The explosion itself is just like from a pyrotechnics library. Somebody set up a bunch of explosions and filmed them and then made the library available. And this one just comes stock with the Unreal Engine. I don't know, maybe a lot of you recognize it. Basically, what we do to start with is we take every frame of the explosion and we put them into an Atlas texture like this. And usually, if you end up making a lot of these, you make a Photoshop action that builds it for you, because it's kind of a pain in the neck to scale all the frames and fit them into the Atlas texture. But anyway, so we start out, let's just say we have one already, right? We start out with an Atlas texture, and we're going to walk through the process of creating a shader that will display each of these frames one at a time to create the, come on, play. Oh well, to create the cool looking explosion. So let's start out really simple. So we have our texture sampler, and here's the texture sampler, and we have our texture coordinates, and they're just plugged right into the sampler. And what we get is just the Atlas as it is, and that's definitely not what we want. We want to show each individual frame one at a time, like this, right? It's got to go over 6 and then jump down 1, and then go over 6 and jump down 1, and keep going like that. So the first thing that we need to do is scale the texture coordinates. When we talk about how to scale them already, right, with multiply, we scale with multiply. So here's our multiply, and we take our texture coordinates, and here is the dimensions of our Atlas. So if we look at our Atlas texture here, we have 6 frames by 6 frames. So here in our shader, we have it's a float 2, remember, data types. 6 and 6, and those are our dimensions, and we divide them by 1 because we're dealing with texture coordinates. Our 1 over 6 by 6, and multiply them by our texture coordinates. Then we just get 1 frame, and that's the first frame of the Atlas Walk. But we want to animate this so that it goes from 1 frame to the next. So the next thing that we need to add is time. So here's our time node, and we're multiplying time by the frame rate that we want. And I'm going to start out with 4 frames per second. This is it's going to be pretty slow to begin with, but I wanted to have it be slow so you could see what was going on to start. And then we'll jump it up to a better frame rate at the end. So now we introduce time. And now we have our Atlas that's scrolling. It's the right size, and it's scrolling diagonally, right? So that's not quite what we want. We still need it to jump from 1 frame to the next. What time does is it progresses linearly and continuously. And what we want to do is step, right? We want to go from 1 to the next and hold on each individual frame instead of scrolling continuously. So we're going to introduce a new node called floor. And what floor does is basically it rounds down. So if my value is 0 and it's going up to 1, floor will force the value to be 0 until it becomes 1, and then it'll jump it up to 1. And then it'll stay 1 until it becomes 2, and then it'll jump it up. So it becomes kind of like this stair-step pattern instead of continuous. So we're going to add floor in. And here's our floor, right? So we're going to multiply time by the frame rate, and then we're going to add floor. So that will make time progress like this. Right? And then what we'll get, now it's continuously going through the frames. However, the problem here is we're still going diagonally through the atlas. So we show the first frame and then sort of the middle frames and then down to the last frame. And it's not showing all the frames. It's only showing the frames that are in the diagonal row. And so what we need to do is split it up so that it's scrolling across. And then once it gets to like the sixth one, it'll jump down and back and scroll across again. So now what we're going to do is we're going to step in X, and then we're going to jump in Y. So here are our texture coordinates. Here's our floor value. And we'll plug that in. That becomes the X coordinate. So here's our append. So here's X. And then for Y, we have our floor here, but we're going to do a floor again so that every sixth value, it's going to round it, and then we'll jump down. So these are our Y coordinates, and this is our X coordinate. And then those get appended together and added to the texture coordinates. And then we use that to sample the texture. Now, there's one other node that I haven't talked about yet, and that's this frac here. And what frac does is if the value gets above 1, it wraps it around and makes it 0 again. And so that's how we're able to go, across, and then when it gets to the end, it jumps back. Instead of just continuously like going off the page, the frac node there makes it so that when it goes off the page, it wraps around back to the beginning. So there's the completed shader, and it allows us to make really cool explosions. And again, here's what the code looks like for generating those UV coordinates that we can then use to look up into our texture sampler to step through each of the frames. Let's see if there's anything I wanted to bring up in here. Dimensions here. That is the dimensions of the atlas. So in our case, in our example, it was 6 by 6. But you can make an atlas that was 3 by 8 or 2 by 12 or whatever the atlas dimensions were. So that's how you make cool explosions. All right. Next example. I call this the lazy artist example. Artists like to be lazy. Or maybe it's saving money at your studio example. In the past, when you were creating assets for different levels, say you had a snowy level and a jungle level and a desert level, you would create rocks with sand on them, rocks with snow on them, and rocks with moss on them. But what this shader allows you to do is to take the same rock and in the jungle apply moss, and in the desert apply sand, and in the Arctic apply snow. That way you can just create a few assets and get a lot of reuse out of them. And what it does is it blends whatever the environment material is, moss, sand, snow, and it adds it to the top of your rock. This is a technique that was made quite popular in games like Skyrim, and you can see a lot of uses of it there. So here we have our textures. On the very top there, we have our diffuse texture for the rock, and then we have our diffuse texture for the moss, and then we have our normal map for the rock and our normal map for the moss. But you can see that only the rock texture and the rock normal are actually wired into the surface root. So the result that we get is only rock. And so what we're going to talk about is how to blend these two together so that we get a nice combination of the environment material on the top and the rock for the rest of it. So you can see these two textures aren't yet connected. So we're going to introduce a new node called LERP. And LERP stands for linear interpolation. And it's basically a blend. I can blend between two different things and get a result that is a nice mix of the two of them. So like the very most basic way to use this is to just plug both textures into it. And then the alpha value that you see here is how much of each of them to blend. And in this case, I just have my alpha value hard-coded to 0.5. So you're getting half rock and half moss. And this is obviously a substance that doesn't exist. So you get this really weird sort of half gray, half green object that is not what we want. But it's the very most basic way of using lerp to blend two different things together. So we're going to do a couple of things. The first thing that we need to know is which direction in our scene is up. And our normal map is relative to the surface of the model. It's in tangent space, which basically means it's an offset of whatever direction the normal is currently pointing. So it doesn't tell us exactly which direction in the scene is up. It just tells us like which direction is like offset from the current normal that we're dealing with. So we need to figure out which direction is up, and that's what this transform vector node is going to do for us. In Frostbite, we deal with world space normals by default, but in Unreal they deal with tangent space normals by default. So we have to transform the normal to world space, which is what the transform vector does. And we're also going to use this mask node, which allows us to choose a specific component of the normal so that we know which way is up. So what I'm going to do is, I'm going to wait for this laptop to catch up to me. There we go. All right, so I'm going to take our normal map, and I'm going to plug that into our transform vector. And what that does is it tells me this normal used to be in tangent space, and I'm converting it into world space. And then using the mask node right here, I'm going to pick the B component, or the Y component, which is, in this case, we're Y up. So Y is the vertical component in world space, and that will tell me what is up and what is down. So if I pass that into my base color node, you can see that now I'm getting white on the top and I'm getting black on the bottom. So this is not the result that I want, but this is what my mask looks like that I'm then going to use to blend. So I need to plug something into my lerp node to blend between the rock and the moss, and I'm creating, my goal is to create a mask that I can then use to blend between the rock and the moss. So that's what I'm doing here. So I'm using the Y component of the normal transformed into world space, and that gives me something like this. I want to adjust it a little bit. So I'm going to add in a couple more nodes. I'm going to add 0.3, and I'm going to clamp it between 0 and 1. Now, one tip here, and maybe some of you that are more familiar with Unreal can tell me about this after. If you're writing a shader in HLSL and you use the saturate function, it's basically a way to clamp between 0 and 1 for free. Like you don't have to spend any instructions, it just does it. If you use the clamp node, and I was not able to find a saturate node in Unreal. Maybe there isn't one, or maybe it just automatically knows if you have a clamp node and it's set to 0 and 1, then it uses a saturate instead. I hope so. But it does. OK, fantastic. Oh, fantastic. OK. So you clamp between 0 and 1. So here, anyway, I'm adding 0.2 and then clamping between 0 and 1 again to just kind of subtly, so let's see, back, oh man. To just kind of subtly adjust the mask so that there's more white. Now the next step that I want to do here, my mask is really blurry, and what we don't want is sort of a really blurry blend between moss and rock. we want to make that sharp. So these nodes here are doing the sharpening. Now this is a good component to use in all kinds of different shaders. This is a really simple sharpen operation where I subtract, let's see, so I subtract 0.5 and then I multiply, this subtract here subtracts 0.5, and then I multiply by the value that I want to sharpen, and then I add 0.5 again. So if you want to sharpen, this is how you do it. You transform it by subtracting 0.5, then you multiply to do your sharpen, and then you add the 0.5 back again. Okay, and then again you clamp between 0 and 1, and that will do your sharpen. So now we have a mask that is really sharp and white on the top and really sharp and black on the bottom. So we can use all of these nodes as our mask. And here's our mask again. And then we can plug that into our alpha value. Remember, when we first introduced the lerp, we just had kind of a hard-coded 0.5 for the alpha. But now we have all of these as the alpha value, and we get a nice blend between the moss and the rock. Now we didn't do our normals yet, so let's plug those in. And this is where it gets really tricky to make a slide that's clear. So I hope there's not too much spaghetti on this slide. But I've got my mask here. And the mask is plugged into the lerp node, which is blending between the two normal maps, and the lerp node, which is blending between the ROS and the moss texture. So pretty cool. And I can replace my moss with snow, or I can replace it with sand, whatever. And the nice thing about this, the other advantageous thing is that I didn't mention yet, is like some artists like to make rocks with no polygons on the bottom, which means that they can only go in one direction, right? But if you make a full three-dimensional rock, you can rotate this rock around however you want. And that environment material, whether it be sand or snow or moss, will always stay on the top of the rock. And the cool thing about that is you can make one rock that's sort of this cool-looking shape and then rotate it lots of different ways, and it looks like you've made hundreds of rocks where you really just have one. And then you can take that one rock and put it in lots of environments, and it looks like you've made thousands of rocks, but you just made one, right? And this shader is what enables that to happen. All right, so again, whoa, that's crazy. Okay. Again, here's the HLSL code that we can use to generate that mask that does the sharpening and creates a blend using the Y vector of the normal that we can then use to blend between the moss and the rock. Okay, so we've gone over 3 examples. We talked about distortion, and we talked about atlas walking, and we talked about environment blending. So the big question is, what do I do with this information? Where do I go next? So what I want to encourage you to do is, first of all, take a look at other games and see what their shaders are doing. You can do some incredible things with shaders. Some of the coolest things that I've done with shaders have been in the last 2 months. And I can't talk about those now because my project is not announced, but I'm hoping to be able to talk about it next year. It's really exciting what you can do with shaders. So this is what I want to encourage you to do next. Look at a lot of other games, see what kinds of things they're doing. Grab a book, go and do Google searches on people that are writing shaders. There are a lot of YouTube videos on people explaining how to write shaders in Unreal, for example. Download the Unreal Engine or use shader effects in Max or Maya. And go out and write some shaders because they're absolutely fun to write, and you can get amazing results. You can really up the quality, the visual quality of your game, and do some fantastic things with shaders. Anyway, thanks very much. And if you have some questions, feel free to step up to the mic. I'd love to help you out with whatever you're wondering about.
Question.
Please go ahead. Speak right into the mic.
Sure. So I was wondering what would happen to like that mossy rock sample if you wanted the rock to animate, like a boulder chasing you down a hallway or something. Wouldn't the moss end up staying on top? So is there a way to like bake it to say, okay, now the moss is always there. This thing becomes an animated model and then rolls after you?
Yes, absolutely. So if you wanted to do that, in my case, I'm transforming the vector from tangent space to world space. So it's always going to be up. So you can rotate the rock and it'll always be up. If you wanted to make a specific rock to do that, you would need to transform the vector to object space, and then it would stay in one part. You'd have to make a specific rock for that kind of an application.
Cool. Thank you.
You're welcome. Yeah.
Hey. So for the distortion example, you're using a black and white mask through RBG to get the 0 and 1 values. you can use a similar effect with the sine wave, but to a certain extent, the spaghetti grows more and more. But on the other side of that, if you use texture samples, at some point you can only use a certain amount of texture samples. So maybe kind of an obvious answer, but which direction would you suggest going, whether it be the texture samples, so it's a simpler way to get your results, or through like using the straight math of sine, which might be less intensive?
That's a very good question. It's going to depend on what hardware you're using. And so the hardest way to figure it out, but probably the best, is to do both and test it. And it also depends on, like you said, you're going to run out of texture samples at some point. Each different hardware platform has a different number of math instructions that add up to the same cost as a texture sample. But it's different on each hardware platform, and it's different in different contexts as well.
Okay.
So it's really hard to know the answer for that without doing it. And so, I would recommend just picking away and doing it. And then if you run into a point where you run out of texture samples or your shader's too math intensive, switch to the other one.
Okay, thank you.
Thanks for the question. Yeah.
You recommended that we read books. Which book do you recommend?
So I have some favorite books that I used to learn, but when I learned it was about 10 years ago, and most of them are outdated. I haven't taken a look recently. How about if I post that on techartist.org? Yeah?
That'd be great.
Okay.
Thank you.
I'll post some recommendations. Yeah.
Hi. So as we saw, you can get into pretty big, kind of scary-looking networks pretty quickly, and there's a lot of combinations of values and a lot of math going on there. And I think that especially for someone first getting into this space, it's sometimes not very obvious what will have what effect, what combination of tools at your disposal are going to yield you the result that you want. Are there any tools or resources that you would recommend for sort of getting to a more intuitive understanding of this is the direction you want to be looking to achieve the result that you want?
Yeah, that's a really good question. One of the things that I was really impressed with, like I said, when I made the illustrations in my slides from Unreal, one of the things that I was impressed with in Unreal is how easy it is to get to documentation from within the editor and for each node. You can click on a node, and I think you hold down Control-Alt. Like, there's a nice little tooltip there that says this is this. But if you hold down Control-Alt and you mouse over the node, there's a bigger tooltip that describes, like, in depth what it does. And you can even click on another little icon that'll take you to the web where there's a page that describes, like, in a lot of detail and gives examples. And I was pretty impressed with how easy it is to access. What you really want is, for this node, give me a list of 15 things I can do with it, right? And I think you can find those kinds of things through those sources with the documentation, and also just by looking at other people's shaders and finding the node and seeing what it's doing for them.
So look at example use cases, explore, see what other people have done with it, and that's a good way to start.
Yeah.
Awesome, thank you.
Yeah, thank you.
Hi, I just have a really quick question. So I've struggled in the past with like parameterizing certain parts of shaders to say, a couple of artists and like making them human readable, like what it does, and like increasing contrast or like pulling specifically on the environmental blending material, pulling back that border by adding or subtracting to the Z up, or shifting that border or kind of highlighting it with the edge or something. And I saw that on the contrast that you outlined, you used you subtracted the 0.5 and then you multiplied. I've also seen it done with a power.
Okay,
and
yeah.
a multiply and then a clamp. Does that accomplish the same thing? Does one of those make a better exposed variable to use, or?
So power, if you think of the value that you're returning between 0 and 1, standard, you just get a linear curve or a linear line from 0 to 1.
Right.
Power will shift it and bulge it. If you plug it into Mathematica or something else where you can graph a function, power will curve it instead of it being a straight line. It'll either curve it up or curve it down. And that is, that's definitely one way to change the contrast. Yeah, like what he said, it's a little more expensive to use a power than to just do subtract, multiply,
That's good to
add.
know.
Yeah.
I mean, you mentioned Mathematica. Is that something that is that like?
Well, you can do it on the web as well. There are a lot of websites where you can just plug in a function and it'll graph it for you.
Thank you.
Yeah, you're welcome. Yeah, please.
This is not directly related to your talk, but I'm curious about how specifically architecturally you guys handle like different input layouts in your shaders. Like if you had a glass shader, if you wanted it on a rig model versus a static model, and how you handle the different parameters.
So we usually split up the shaders and make everything unique for dynamic things like characters. They'll have a unique library versus shaders for static things like rocks. Is that what you're asking?
Basically, so
Okay.
you would end up duplicating things probably.
So one thing that I didn't really get into is you can take chunks of these shaders and make them into like subgraphs. Well, I don't know. In Frostbite, you can do this. You can group it and then make that group into a single node. So then you can share those nodes across different networks. You'd make a unique network for dynamic versus static, but they could share elements of each other.
Okay. Okay. Thank you.
Yeah. Thank you. All right. No more questions. Thank you very much, everyone. I really enjoyed talking with you today.